start by recording it so that we have the recording. I'll start with inverses, and then what we'll do is we'll go further and we'll do the inverses of the trigonometric functions, and then we'll define the exponential functions and their inverses, which are the logarithms. So the definition of one-to-one function, and I'll do one more example where we do all of the calculations. The actual definition of one-to-one is if x1 doesn't equal x2, then f of x doesn't equal f of x2, which means that unique points go to unique images in the function. This also means that we have the horizontal line test. Which is similar to the vertical line test in calculus 114. The vertical line test says that the curve in the plane is the graph of a single function if and only if no vertical line intersects it more than once. We have the similar definition for one-to-one function. F of x is one-to-one if and only if no horizontal line intersects the graph of f of x more than once. And of course, the two standard functions you want to use, you don't want to use complicated functions when you're trying to do this. We will eventually extend this to more complicated functions, but at first, when you're trying to look at the properties of this, you should pick basic standard functions from your list of standard functions, power functions, root functions, trigonometric functions, etc. Ones that you should already know what the graph looks like. I missed 0. So if we look at this guy, this is x squared versus x cubed. The odd powered power functions are going to be one-to-one, and the even powered functions are not going to be one-to-one. If we look at horizontal lines, then these are good to go. But in this case, we have 2 points, say -1 and 1, for instance, which are not equal to each other, but their images are both equal to 1. And so this is bad. What we want is one-to-one functions. And yes, we discussed last time that, especially with the trigonometric functions, which I'll do today, if it's not one-to-one, sine is not one-to-one for sure. It's a wave that goes over and over again. So how can it be that your calculator has a sine inverse function? What we do is we restrict it to a domain or an interval where it is one-to-one, and then we can invert the function on that interval, which we'll do later. The other properties we have is if I am a one-to-one function, what I want to do is be able to invert that process, and we call that the inverse function. So definition. A one-to-one function. So you already have to have that it is one-to-one. And then we will notice from A to B is how we will write this. If this function is one-to-one on A, then the inverse function f minus 1 from B to A. So I already noticed that the domain of f is the range of B, and the range of f is the domain of B. They interchange domains and ranges. Is defined as f inverse of y equals x if and only if f of x equals y. And this is for all y and b. So what we're doing is, this is extremely important, this definition. Everybody just nods their head and goes, yeah, yeah, yeah. And then we give clever, tricky questions like the derivative formula for some of these, or calculating values. And the way that we're going to calculate values is we need to find values in the function and compute those points, and then just reverse the points, and then that gives us the values of the inverse function. I'll do an example all in one. We'll verify the cancellation formulas as well. So the thing I didn't do last time is the cancellation rules. Really didn't want to write cancellation laws. So what are the cancellation laws? Basically, this is composition of functions. Did I forget anything else? I don't think I forgot anything else. And then we'll do the algebraic finding inverses. So this becomes extremely important, the domain and the range, when we go to actually calculate it, specifically trigonometric functions. They're going to try, and they being me, I guess, or the coordinator who makes all the assignment questions, Sunil Baran. They're going to try and trick you with the trigonometric functions, and they're going to say, what's sine of sine inverse of pi over, or 5 pi over 6 or something like this. That one you can just, pi over 6, you can just cancel them. If we have 5 pi over 6 or some larger value outside of this range, then we can't just cancel these off. So what this is saying is, if you have f inverse following f of x, this is f inverse of f of x. So what we're doing is we're doing f first, and then we're applying f inverse. And when you do that for any point in the domain of f, this will just give you x. But this is specifically for all x in the domain of f. You can cancel the other way. If I do f following f inverse, if I do f inverse first and then do f, you get to the same point. I view it always as an airplane ride. I go to Europe, I mess around in Europe, they kick me out eventually, so they're like, you need to go back. And so I take an airplane back. The airplane ride back is not the same plane. It was the inverse plane. But where do I end up? I started here in North America. I go to Europe, I come back, and I've ended up at the same spot. So when you take the function and then the function's inverse, you end up at the same spot. This is the same thing. If I have f following f inverse of a point y, I change this. A lot of the books will put x in both cases. Yes, we're using x as the independent variable, but to make sure that you realize that it's a different domain a lot of the time, this will be, by definition, f of f inverse of y. And that is equal to y. So same thing, if I start in Europe and then I come to North America and then I take it back, then that will end up in the same spot. This is for all y in B, the domain of f inverse. This condition here will become extremely important when we do trigonometric functions, because they will try to do, for instance, if I have sine inverse of sine of 5 pi over 6 is not just 5 pi over 6, and you're like, well, why not? You just said I could cancel them. What that's essentially doing is saying that functions and their inverses cancel each other. And this will be in general when we're doing this algebraically. Yes, as soon as sine and sine inverse, or arc sine, I will probably call it, it doesn't really matter. Why? Because 5 pi over 6 is not in the interval negative pi over 2 to pi over 2. But sine inverse of sine of pi over 6 is just equal to pi over 6, since pi over 6 is inside the domain of f. Because what we're doing is, we saw last time, and I'll go over it again, sine is not 1-to-1 on its entire domain. So we're going to go from negative pi over 2 into negative 1, 1. This is the A and the B. And so what does that say? Sine inverse must be the function that goes from -1 to 1 into negative pi over 2 to pi over 2. And so I can only cancel when a value is inside the trigonometric, or in this case, sines 1 to 1 domain is negative pi over 2 to pi over 2, cos is 0 to pi, and arctan is open interval pi of negative pi over 2 to pi over 2. They have slightly different domains where they're 1 to 1. Yes, and that's exactly what's going to happen originally. Don't let them try it. You have to, everyone just says this, these cancellation laws. And the first functions we give you, if you have a 1-to-1 function, there's cats running around. She keeps opening the door. I'm trying to keep it closed. But sometimes what we'll have is, if we look at a general nice linear function, the first ones I looked at, if you look at f of x equals 3x plus 5 or something that I did last time, then this is going to be a function. F is going from R into R. It's both domain and range. It's 1 to 1 on all of R, and it goes into all of R. So F inverse is going to also go from R to R. And so F inverse following f of x in this case will equal x for x in R, and f following f inverse of x will equal x for x in R. Or I like to emphasize, when we do it the other way, y. But there is no restriction because the domain of the function was entirely R and its range was R. So when I flip these, the domain and range of f inverse is also R. So there are no restrictions. But if this is not R, watch out, because they're going to try and bait you into saying, oh, you can just cancel, and they just touch each other. They cancel when they touch each other. When I have, if I'm trying to say what sine of sine inverse of x, then yes, I can just write this as x, but we're assuming every time that x is actually in -1 to 1. There is a restriction, so you can't just cancel in these cases unless it is. How do you find the values then? You use the unit circle and you do it one at a time. I'll do this when we get closer to the trigonometric functions, but this is the first thing. The cancellation laws only work when you're on the domain of A or F, or in the domain of F inverse, depending on which one we're starting with. And they'll immediately try to bait you, and you're like, I thought you said you could cancel. And I know the most important part is always only in certain sets can you cancel these things. So what is this one, by the way? Sine of pi, 5 pi over 6 is what? 1/2. Sine inverse of 1/2 is pi over 6. So the real answer is pi over 6. You have to use the unit circle values. Is how I'm computing that. I'll do it once we get to the trigonometric function and we discuss them more in detail. But be careful, they're going to try and trick you, and this cancellation law only works on the domain of F and or the domain of F inverse. Good. What else do I need? So how do we find the inverse of a relatively tame algebraic function? We have algebraic and transcendental functions. The transcendental functions we're going to get are the trigonometric functions, the exponential functions, and the hyperbolic functions, which are linear combinations of exponential. They all have inverses, some of them on all of R, some of them not on all of R. So we have to restrict, and then we have to be careful. For the basic algebraic functions, usually it's 1 to 1 on most of the real number line, and then so you don't have to think about this cancellation, you just can. For these weird transcendental functions, we have to use the definition. We have to find out the intervals that they're invertible on, and then we can only cancel in those intervals. Step one. What do we want to do? We want to write y equals f of x. In this case, a lot of the books will say interchange x and y, but I don't see the point. We'll do this at the end. You've been trained to solve for x in equations your whole life, so we're going to solve for x. Step two, or this could be all in one step. Solve for f for. I have an old grumpy cat. I know, hey, this one, and a young one. And the young one keeps bothering the old one. Oh, here comes the, so this one's the grumpy one that's making the in the background. And this little shit. And this one's the one chasing her around, Alice. So when you hear growling in the background, it's because this one is teasing the other one. Younger sisters. So solve for x. Oh, you can see already she's teasing her. Stop it. Then what do we want to do? Step three. Interchange x and y once you've done this, and then you have the inverse. And I will just lazily write x interchange y, and then this implies we have y equals f inverse of x. I will do this for a couple of functions. So, and I'll do this at first, I'm going to do this for functions that we can invert. And then eventually there are functions algebraically. And then there are functions where even though it has it's one-to-one, we know it has an inverse, but we have no algebraic way of inverting for transcendental functions. You guys, enough. They're never going to stop. I can yell as much as I want, they never listen. Once we have transcendental functions, or these functions that I can't algebraically solve for, we need to stick to the definition to compute values, etc. But for now, what are we going to do? Example. Show, first of all, f of x equals, it doesn't matter, let's use one. So show this function is one-to-one and find its inverse. Notice that the algebraic operations I use to show that the function is one-to-one are identical to the algebraic operations I do to solve for, I have the internet up still? Why is it bling-blinging me? Just a second. Oh, one of you sending your accommodations. Let me delete that. I don't need notifications while we're doing the Zoom meeting. The cats will distract me enough. So what do we want to do? First, we show it's one-to-one. And when we go back, we don't use the silly definition that the book of the gives. This is the definition of one-to-one. But this is how we actually compute and show things are one-to-one, not using the definition, using the contrapositive, which is logically equivalent to the definition. So every time we want you to show that this is one-to-one, if you didn't start off by assuming I have 2 points where their images are equal, you're doing it wrong, because what we want to do is assume that their images are equal and show that the values are equal. This is just going through the motions for the algebraic ones at first, and it's not that bad. All you want to do is do the inverse operations and then solve for x essentially, or cancel everything off, and you will see that x1 equals x2. Those algebraic operations are exactly the same operations I'm going to do to find the inverse after that. So what am I talking about? First, we show it's one-to-one. So I assume we have x1 and x2 inside R, or my domain of F in this case. But this is power function, which has been shifted and scaled slightly by 1/5. And so the domain of this function is all of R. So the cancellation laws will work for all of R, and the inverse will be defined on all of R as well. But such that f of x1 equals f of x2. Well, that immediately gets me something. And this is by the definition of f. We know what f is. It told us what f is. How can I do this? I know what f is, so put those values in there. This says that x1 to the 7 minus 2 over 5 has to equal x2 to the 7 minus 2 over 5. And when I start solving, and when I start doing differentiation, when I'm using quotient rule, power rule, and all these, which ones do I use first? The last algebraic operation used to build the function is the first thing I want to take the derivative of, or it's the first thing in this case that I want to unwind. So the last thing I did to build this function was I took x, I power 7'd it, I diminished it by 2, subtracted 2, and then I scaled it by 1/5 or multiplied by 1/5. In that story, the last thing I did was multiply by 1/5. So the first thing I want to do to unwind this is multiply both sides by 5 so I can cancel the division. What's the opposite of division? Multiplication. So multiplication and division cancel each other, just like sine inverse and sine will eventually cancel each other. They're inverse operations of each other. So this is going to be, I immediately know that I want to multiply by 5 on both sides. And again, I guess I can do it in brackets. What that's doing is I'm multiplying both sides by 5. These will then cancel, 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 cancel. And I get x1 to the 7 minus 2 is equal to x2 to the 7 minus 2. Now, the last thing that's happened is I've subtracted 2 from both sides. How do I cancel subtraction? Addition and subtraction are opposites of each other. So I want to clearly add 2 to both sides. When I add 2 to both sides, the 2 and the -2 will cancel, and I'm left with, what is this really going to do? This will be x1 to the 7 minus 2 plus 2 equals x2 to the 7 minus 2 plus 2. The 2's will now cancel. Cancel, 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 cancel. I'm writing the intermediate steps that they don't write down a lot of the time in, or do in your head in the orange. And then the consequence of this is you get x1 to the 7 is equal to x2 to the 7. Now I powered 7 something. What's the inverse of that, or how do I unwind that? Nth roots, turns out, are the inverses of power functions to the power 7. So I want to take the 7th root of this. What is that going to get for me? If I take 7 roots of both sides, this will give me technically the 7th root of x to the 1 to the 7 equals the 7th root of x2 to the 7. These are now going to cancel. And that leaves me with what I wanted. So if we assume that f of x1 equals f of x2, I got that that implies that x1 equals x2. Therefore, f is in 1-to-1. And hence invertible. I.e., f inverse exists on its domain, which is all of R. How do I find f inverse of x? I use the exact same algebraic operations. Step 1, we write y equals f of x. What does that mean? It's the same steps even here. What did I use? I said I had to show f of x1 equals f of x2. How do I get a starting point? Well, the definition of f. That says I should be writing y equals x to the 7 minus 2 over 5, because that's f of x in this case. Now what should I do? Look at the algebraic operations. Then we multiplied by 5, we added 2, and we took a 7th root. We're going to do the exact same thing to solve for x. Multiplying by 5, I'm going to get 5y equals x to the 7 minus 2. I'm not doing the intermediate steps anymore. I just multiply both sides by 5, like this, and the 5s will cancel. Then what? Well, look at what I did to solve for the inverse, or showed it was 1 to 1. Now I want to add 2 to both sides, it looks like. So I will. This says 5y minus or plus 2 is equal to x to the 7. The negative 2 and 2 will cancel on the right hand side, and we've added 2. And now what do I want to do? I have a power 7. It's odd, so I can invert 7th root. If I 7th root both sides, that gives me the 7th root of 5y plus 2 is equal to x. That's the inverse function. Step 3, interchange x and y, and this gives me f inverse of x is equal to the 7th root of 5x plus 2. This is how we find the inverse of algebraic functions. So check, you can check this always using cancellation. What do I mean by that? Well, f following f inverse of x is going to equal, by definition, f of f inverse of x. How do I do this? By composition, I do the inside first. So f of, what does f inverse do? It takes me to the 7th root of 5x plus 2. Where do I put that? I put that wherever x is in my original function. So what's my original function? This guy, x to the 7 minus 2 over 5. So this becomes the 7th root of 5x plus 2 to the power 7 minus 2 over 5. I put this thing wherever x was in the expression for f instead of an x. Now you'll immediately see that the 7th roots cancel. So this is equal to 5x plus 2 minus 2 over 5. Oh, magic. The 2's cancel. This gives me 5x over 5, which leaves me with x. Sorry, the cat's running around. It's like I have 5 cats and now I have allergies to cats. So thank you. Yeah, thanks. That won't stop. The irony of collecting cats and being allergic to them, apparently. I'm not getting rid of the cat. You can do it the other way too. F inverse following f of x is going to equal what? I've only got 20 minutes, I got to speed up. This is going to be f inverse of f of x This is going to be f inverse of f. What was f? X to the 7 minus 2 over 5. Then what do? This is going to be f inverse. So I put that thing wherever there was an x in this. So this will be the 7th root of 5 times x to the 7 minus 2 over 5 plus 2. First of all, we see that the 5's cancel. This is equal to the 7th root of x to the 7 minus 2 plus 2. The 2's cancel. And this is equal to the 7th root of x to the 7, which is just x. This is how we use the cancellation laws, how we algebraically solve for f inverse, and how we show that functions are one-to-one. Again, notice that the algebraic operations to show that the function is one-to-one are identical to the algebraic operations I use to find the inverse algebraically. And then all of those operations should cancel each other when we do both of them, both directions. The last thing I need before we do all the transcendental ones is theorem. So this is going to be the derivative. Fruit flies survives in the winter in my house somehow. So what this is saying is this one would be obvious when we can actually invert and find the inverse. Then I can just take the derivative. So if you look, all I did was we now have the inverse function. If I just view that as the inverse function, and I can solve for it, I can just find the derivative this way. So the theorem's not necessary. But when we have weird transcendental functions or functions that I know are one-to-one, but somehow I can't algebraically solve for them, which is the case quite often, we want to know how to compute values in the derivative. The derivative is the rate of change. So I still want the rate of change of the inverse function, even though I have no algebraic formula for it. How are we going to do that? This theorem is going to tell us how to compute these things. And the book writes it horribly usually. So I will try to make the notation a little bit easier. Let f of x be one-to-one. Do it this way. Let f be one-to-one on an interval I. Assume f of x is not 0, and recall that our definition of inverse, f inverse of y equals x if and only if f of x equals y. That tells me who this guy is. X equals something horrible, f inverse of y, and y equals something, f of x. And then the derivative so now that's the prime. Or the way I would like this even better is I'll write it the same way the book does, but in Leibniz notation, the derivative of f inverse of y is equal to, the book will write it like this, 1 over f prime, or the derivative of f inverse of y. But what they're really doing is I'll write it the same way that the book's writing it. They're using Newton's notation. So it's just we need brackets. So the inverse function derivative at a point y, because now we're in the set B. This is equal to 1 over f prime of f inverse of y. It's like, what? That looks like a horrible notation, but remember, what is f inverse of y? It's just x. And this is the formula you want. Cut out that middle section and just ignore it. what this is saying is, which is weird, the inverse of multiplication is division. And so now what they're saying is, if you want to compute the derivative of the inverse at a point, it's 1 over the derivative of f at the related inverse point. Let's do an example of that. Look at the function that we just had. F of x is x to the 7 minus 2 over 5. And we now know the inverse is f inverse of x is equal to the 7th root of 5x plus 2, if I remember correctly. Yeah. So we could just take, with the chain rule and everything, we could just take the derivative at a point. So if I want to know what is f inverse prime of 1, say, what the theorem is saying is this should be equal to what? They're saying, so first of all, what I have to ask myself is this. F inverse, I should have cooked up a nicer value. Is that going to be okay? We'll see. What's in F inverse of 1? I have to use the definition of inverse if and only if f of x equals 1. So which value is going to do that? I have a little bit of experience with this, but if I take x to equal the 7th root of 3, then what am I going to get? Then f of the 7th root of 3 is equal to the 7th root of 3. Oh no, I want not 3, I want 7th root of 7. I'm making the example up, so now I'm doing calculations on the fly. If I do that, then this will equal the 7th root of 7 to the power 7 minus 2 over 5. I was just going to cook it up so that I get, I'm still doing it wrong because I can't add in my head. I'll go through it once I have the number right. I want it to be, I don't know, it was 7. I want it to be a 5 over 5 is what I was trying to get. Then I'm going to get, this is the 7th roots cancel. And I get, I just can't do 7 minus 2. 7 minus 2 is 5. This gives me 7 minus 2 over 5, which is 5 over 5, which is 1. If and only if that says then f inverse of 1 is equal to the 7th root of 7. So now I can use that value to compute this thing, the horrible derivative. That says that, and what is f prime of x? F prime of x is just what? 7 over 5 to the power x to the 6. This tells us by the theorem that f inverse prime of 1 is equal to 1 over f prime of the 7th root of 7. Which is what now? I can compute this. This is 1 over, give me that, give me that. Pushing around a pin on the floor just to make noise. Kitty. Here, we can have this. Which is going to be what? 7 over 5 times the 7th root of 7 to the power 6. Some horrible number. But this is how I compute the derivative of inverse functions. In this case, I can compute these on the homework assignment. If you do this hint in my lecture notes, I think it's the same problem. in there. So you can go look at this and the numbers work out slightly nicer. But this is a horrible game that they're trying to play. In this case, I could cheat because I can actually find the inverse formula of, or I can find the formula for F inverse. In general, I can't actually solve for this, but I still want to know what the rate of change at certain values are. And this is how we get at that with this theorem. All right. So now we have to do the trigonometric functions and then the exponential functions. I'll do the trigonometric ones quickly because I'm assuming you've seen the trigonometric actual functions. And then last time what we did, recall last time, we went through and then somebody asked if it's not one-to-one, do we restrict? So these are the places where making the trigonometric functions one-to-one. Last time we restricted them all on these intervals. Why did we do that? So that I can now find the inverse of each of these functions. Yeah, you don't need in there, kitty. I know, what's that? Okay. Okay. This one, little shit disturber. I know you're wrecking everything. I know what is that. Oh, that's okay. Yeah. And I will focus on sine and cos and tan. The inverses of the other ones you can worry about later, but I won't test you on these ones. We restrict them the same. So where is this? So 1, the sine function. An arc sine. What we have is, I'll draw them both together. And we did this last time where they were one-to-one. But what we're going to have is sine from negative pi over 2 to pi over 2. We have the sine function goes from -1 to 1. Therefore, we're going to get -1 to 1. Then we're going to have pi over 2 and negative pi over 2. And this acts like reflecting across the line y equals x. So we're going to get, this will be sine x, and this is sine inverse of x, or arc sine. The synonym, arc sine. Algebraically, what does that say? That says that sine is going from negative pi over 2 to pi over 2. So when we do these cancellation laws, watch it, into -1, 1. So sine inverse has to be the function that goes from -1 to 1 into negative pi over 2 to pi over 2. And we compute values this way using the unit circle. To find arc sine of a value, arc sine of 1/2 is pi over 6. How do I know? 1/2 is in my domain of sine inverse, and this equals what we're asking. I use the definition, if and only if, what? Sine of x equals 1/2, and then the unit circle tells me that sine of pi over 6 is 1/2, if and only if sine inverse of 1/2 is pi over 6. So this is how I'm computing the values of, this is 1/2. This value will be pi over 6 in the inverse function. Also, what we're saying is, be careful, sine of sine inverse of y equals y if and only if y is inside -1 to 1, and sine inverse of sine of x equals x if and only if x is in -pi/2 to pi/2. And then immediately, yes, whoever said it is Clarissa. As soon as somebody tries to bait you into saying, can you can't, and then they'll just try to give you sine -1 of sine of 5pi/6. And then you're like, well, I'm just allowed to cancel. And then so it should be just 5pi/6. And no, it's not, because 5pi/6 is not inside this interval -pi/2 to pi/2. So what do I do with this instead? This is wrong. What do I do instead? Well, I have to do sine inverse of sine of 5pi/6. So I use the unit circle again. 5pi/6 is over here. That's the 2pi/3 one. I want to erase that. So if this is 5pi/6, my angle, we know that at 5pi/6 that cos is -√3/2, and this is 1/2 still. So sine of 5pi/6 is 1/2 from the unit circle. Therefore, this says that sine inverse of sine of 5pi/6 is equal to sine inverse of 1/2, which is pi/6, which I just calculated above using the unit circle. So this is the correct computation. And they're going to try and bait you into that immediately. You can't just cancel unless you're in that interval, depending on whether it's sine first or sine inverse first. So that's sine. Don't be tricked by this. Or cosine. Or cosine and arc cosine, these inverses. Well, what I have is, I see that I should draw them to make sure that they're 1 to 1. In this case now, we're going to go from 1 to here to here. There should be pi/2 and 0. So from 0 to pi now I'm 1 to 1. No horizontal line intersects. So therefore I'm going to get now, no, it should be pi/2 pi. So here I'm going to get this, and then I will get from -1 to 1. Or sorry, that should be, yeah, that's right. So what are we going to get? Algebraically, this says cos goes from now the interval 0 pi into -1 to 1. And so cos inverse should be going from -1 to 1 into 0 pi. So I didn't label them. This is cos x, and this is cos -1, or arc cos. This is pi/2. This is partially, it's pi. So they're slightly different domains. And again, that says that you can cancel. So cos of cos inverse of x is x, which acts as just canceling. Cancel. As soon as they touch, they annihilate each other. But that can only work on what? For x inside -1, or sorry, this should be y for emphasis. For y in -1 to 1, and cos inverse of cos of x is equal to x for x inside 0 pi. So again, you can't just cancel them off. Make sure that the cancellation laws, these are the cancellation laws for cosine. And then the last one we have, because I want to do the, oh, I'm already over almost. I'm 2 minutes over. So I didn't quite do the exponential functions. I'll do this on Thursday for sure. But the last one we have, and then I'll let you go, tangent and arctangent. Arctangent is extremely important in this one when we do partial fraction decomposition. So in this case, again, we're looking at these two things. We see that now it has a vertical asymptote at negative pi over 2 and a vertical asymptote at pi over 2, and tan of 0 is 0. And so what we're going to get is a horizontal asymptote, limits at infinity in the positive direction of pi over 2, and a horizontal asymptote in the negative direction of negative pi over 2. And we're going to get arctan x versus tan x. This is when tan is 1 to 1. And then we invert this and we get arctan. Notice that what this is saying is the limit as x approaches positive infinity of arctan x equals pi over 2, which says y equals pi over 2 is a horizontal asymptote. This is important when we start doing limits of these transcendental functions. This is a new bounded function. Right now you have bounded functions. Sine and cosine are bounded between -1 and 1. And now we have arctan is bounded between negative pi over 2 to pi over 2. I'll discuss this later. But for now, squeezing in, if you have to go, you have to go. But the exponential function and logarithms, the inverse of exponential. What are they? I'll just draw these quickly and show you the problem we're now going to have. These are transcendental functions. And so the trigonometric functions are transcendental. And so we didn't algebraically have a way of solving for x in those ones. So we had to give it a name, arc sine x or sine inverse, and arc cos and arc tan, because we have no way of algebraically solving for sine. We can't just write y equals sine x and then solve. There's no algebra to do. Same thing for the exponential functions. And all exponential functions are going to be invertible. If I have a to the x, they're all going to go through 1. You can see that they're 1 to 1, but I have no way of algebraically solving for it. If I write y equals a to the x, how am I supposed to solve for this? So this is where we get the name. If this is y, if f of x equals a to the x, then f inverse of x is going to be called logarithm, and it's going to look like this. Reflection about the line y equals x. This will be log base a of x. This is how we're defining them. And then you can run away now. But we have cancellation laws. This says that if you have a to the log base a of x, that is going to equal x, because that's f following f inverse. And if you have log base a of a to the x, as soon as they touch each other, this is going to equal x. And it looks like they're canceling each other, and they are. This is the cancellation laws for the exponential functions and logarithms. So on Thursday, I will start with the exponential functions and all of this, and then we'll take the derivatives and everything else of these new functions. So the first categories of transcendental functions we have are the trigonometric functions, focusing on sine x and its inverse, cosine x and its inverse, tan x and its inverse. Now we have the exponential function a to the x. In particular, we'll get e, this magic number, e to the x. And then the inverse of this is called logarithm. In particular, the inverse of e is called the natural logarithm, ln x. And this is how we compute values of the inverse function, is by computing values in the exponential function and then playing this definition game. So on Thursday, we'll do more exponential functions and a bunch of examples. And then we will carry on. I'm going to guess I might sneak in the hyperbolic functions as well. There's 3 main categories: trigonometric functions, exponential functions, hyperbolic functions. Now what we want to ask ourselves is we're going to get a huge category. There's 6, but I have 3 trigonometric functions, sine, cos, and tan. Then I have 3 inverses, arc, sine, arc, cos, arc, tan. They all have derivatives. That's 6 more functions just for those. The trigonometric functions, we know the derivatives already from 114. We now want the derivatives of the inverse functions. Then I have exponential functions and logarithms. I want the derivatives of those. Then I'm going to have sine hyperbolic, cos hyperbolic, tan hyperbolic. Then I'm going to have sine hyperbolic inverse, cos hyperbolic inverse, tan hyperbolic inverse. And then I'm going to want the derivatives of all those things. And then in this class, we're going to do integration. So then I want the integrals or antiderivative of all of those categories of functions. So this is just going to explode in your mind right away by Thursday, what you're asking yourself every time. Every time I have a new function, what's the derivative essentially? And now that we're in 115 for sure, you should be scared. There's only 2 ways to motivate people, fear and reward. And there's going to be very little reward in this class. The reward will be I'll try to be nice on exams. But fear should be the motivator. There's only 2 ways to do it. Yeah, so this is going to explode. This is the problem with 115. Not only do we get new techniques and new things that you have to know, we're going to get a whole new alphabet or lexicon of functions. And every time I give you a new function, you should ask yourself, what's the inverse of that function? What's the derivative of that function? What's the derivative of the inverse? What's the integral of that function? What's the integral of the inverse? We're going to get all kinds. It's in my lecture notes. I have it set up in there. You can go check. But on Thursday, we will start opening up that big bang of the new transcendental functions and their inverses and their derivatives and their integrals. Try to have a good day. I'll see you on Thursday.